Everyone, Ramel Basat here. Today I'll be talking about our probabilistic approach to network telemetry. And this work has really been enabled by the programmable devices that we now have. Like we have a lot of different vendors that are working on these, and in academia we created a bunch of cool works here. But this is not just an academic dream. So we're now seeing these programmable switches, for example, replace existing switches in major companies. And one of the killer apps for these switches is telemetry, right? So telemetry is about figuring out what's going on with the packets. So I want to know things like, is there a congestion or queue buildup somewhere in the network? Do their routing passes taken by flows agree with the policy? Like maybe I want everything to go to a firewall or something. Which hops have high latency if I see high end-to-end latency, and so on. And to that end, we have the INT protocol, or in-band network telemetry, which is now becoming standard. And the idea of INT is really conceptually simple. So if we want to collect information, let's say that I want to know what was the path taken by a flow, I can just add this information to data packets, right? So we can collect the switch ID. So the way it works is something like that. The first hop on the path, it's called the INT source. So it can be the ingress switch or the end host. It will add a piece of information called the INT header. Now the INT header tells the other switches on the path what we are collecting, switch IDs in this example, and now the source can add its own switch ID and send it to the next packet, the next hop. The next hop will read the INT header, figures we're collecting switch IDs, add its own, and so on, until it gets to the last hop that removes this information from the packet. So this protocol is transparent to the sender and receiver, and now that we have the protocol, we can figure out the path. Right, so INT is not just for passes, it's really general. You can use it for large variety of measurements like queuing and latency measurements. It's already running in production in major companies like Alibaba, but it also has high packet overheads. So all this information we add to packets adds up, and this creates a few problems. So first, it can degrade the goodput of long flows. And the reason for that is the more bits you add to the packet, the less bits you can put on the payload without exceeding the MTU. So we would need to send more packets to transmit the same amount of information. But also it increases the processing time at the switch, because now we have more bits to process. So we're gonna spend more time at the switch. And also, all of this information that INT generates, we need to collect it, which can overload the network and process it. So that's like a lot of work there. So to that end, we proposed PINT, or probabilistic INT. And the goal of PINT is really to collect the information that we care about, but while minimizing the bit overhead. And our insights in PINT, like the reason why we think we can improve over INT, is that in many cases, we don't actually need all of the information that INT collects. We don't need all of the per packet, per hop information. We need some aggregated form of them, and this is what PINT gives us. And PINT is implemented in P4, we open source it, but let me explain why we should use a probabilistic approach, right? So what we want to do is we want to reduce the bit overhead on packets, and this comes at the cost of approximation. And you may think of approximation as something like in this figure, but we have approximations with provable guarantees, and we have different types of approximations. The first is numerical approximation, so maybe I will not tell you what was the exact latency that you asked me about, but I will give you a good approximation of it. And this is usually okay because we only care about significant latencies or when the latency change a lot, and we can actually capture that. Also, in other cases, like if you want to know the path, we may need multiple packets to do so, and not like INT get it from the very first packet, but this is also usually okay because flows usually have multiple packets, and we don't need that many before we can give you the path. Right, so let me give you a couple of examples of how we use PINT. And the first is congestion control. And an algorithm from last year's SIGCOMM for congestion control called HPCC is using INT. And what it does is, let's say this is the path, then at each hop, we collect some queuing statistics. And now it determines the sending rate for the end host to be some function of the bottleneck, right? Some function of the maximum queue in the path. Now, what PINT does is it moves the computation of this formula from the end host to the switches, right? So we have some approximation of the formula of the local queuing statistic, and now we can only track the maximum along the path, which correspond to what is the right sending rate so that we will not overwhelm the bottleneck. PINT uses probabilistic rounding. So the idea is that we will have some error because we reduce the bit overhead. Sometimes we would use a higher rate, sometimes a lower rate, but on average, this will cancel out. So after we collect a bunch of these feedbacks, we will converge to the right sending rate. And this is what it looks like, right? So you can see here that especially for the long flows, we can actually improve the performance a lot because now we use only a fraction of the overhead, right? So here we compare INT-based HPCC with PINT-based HPCC, but we also see that we don't hurt the performance of short flows by a lot. So the fact that we have this rounding is not catastrophic even for short flows. PINT also can probabilistically decide whether to act on a packet. And the idea here is that we may want some of the packets to serve other queries. And what we saw is that we can, for example, run HPCC with a feedback that comes in about 1 in 16 packets and still get comparable results. And the reason for that is we will still get multiple feedbacks per sending window, so it doesn't affect the performance by a lot. Okay, let me give you another example. This is for path tracing. So we want to collect the switch ADs, right? So INT does that by collecting switch ADs on all hops. But PINT can actually reduce the bit overhead by sampling, right? So you can think of it as maybe I'm sampling one switch AD, but for each packet, but we can actually do better than that. We can use coding to reduce the number of packets we need for a given overhead by a lot. And we can even use just a single bit per packet. And what we saw is that even with a single bit per packet, we can actually improve over the existing techniques that use 16 bits. Right? So we require only 1 bit and we still give you better performance. And I'm going to give you just intuition as to how coding can help here. Right? So let's say that I want to figure out these two path hops, A and B. So what this baseline of sampling a hop would do here is it would always get some information on the first packet, like maybe the identifier A. But now until we get the other hop ID, we will on average need 2 more packets, right? Because we are equally likely to sample A or B. So in expectation, just sampling would require 3 packets. In contrast, if we with probability 1/2 do sampling and otherwise write the bitwise XOR of both identifiers, we can actually improve because now if the first packet comes in with the identifier A, then we are more likely to terminate on the next packet because either we get B and we're done, or we get A XOR B and we can also infer B because we already know A. So this reduces the number of packets we need in expectation, and we can optimize the algorithm. So what else do we have in the paper? We have a bunch more probabilistic techniques. We have performance guarantees for our algorithm. So it means like we can give you some bounds on how good the approximation is or how many packets we need to figure out the path. And we also have support for concurrent queries, so you can run some of them in parallel. And this is it. Thank you very much. And if you have any questions, I'll be happy to take them. Thanks.
All right. Thanks, Ren. That was awesome talk. Again, attendees, if you have questions for this talk, please use the Q&A tool or the Slack channel to post your questions. And in the meantime, I'll ask some of the questions that we have already. So the first question is, and maybe this is already answered, but I'll still ask because not everybody is on Slack. So is PINT tailored just for HPCC, or this approach is suited for other INT works as well?
No, so this is one example. So we actually gave 3 use cases in the paper. HPCC was one of them, but we have a more general framework.
Okay. So other question that I have, and this is a bit more complicated one, is that the PINT paper or the solution requires some multiplication and division operations. And these operations are not natively supported in the data plane targets. And you have techniques of approximating them using whatever ALUs that are supported in the pieces switches. So my question is like how generalizable these techniques are, and how much do they affect the performance of PINT overall?
So I think like since the algorithms in PINT already have some approximation error, we can actually take this approximate operations, multiplication and things like that, and bound the overall error. So you wouldn't even know that this wasn't natively supported.
Okay. So I have one more question coming from Diman. And the question is, first, there is a compliment. This is a nice presentation. And then the question is that, have you implemented this on any SmartNIC? And if yes, then which SmartNIC did you use?
So we have not tried implementing it on a SmartNIC.
So maybe I can modulate this question as like, is it possible to implement this on a SmartNIC, and what challenges do you see doing that?
I'm not an expert in SmartNICs, but I don't see any fundamental limitation that would prevent it. Like, I think it should work.
Okay. Yeah, I think, I think I have one more question. So you get a performance boost by specializing for a less generic set of INT requests. So what are the typical requests you are now no longer able to answer, and how much your performance benefit would you have to sacrifice to support those things?
I didn't get the question.
So I think the question is that your performance boost is coming by specializing it for a less generic set of INT requests. So if you expand that, like how will that affect the performance?
So I think like one of the things you have to do when you use PINT is you have to figure out what type of, what specific information you are looking for. So if you think of INT, it basically collects all the information, then you can hindsight figure out what you want to run. But if you use PINT, the way we can reduce the bit overhead is by doing the aggregation in the network. So you need to know in advance what type of query you're interested in.
Thanks, Ran. There is a question in the channel, in the Slack channel. Does PINT have fixed header size? And what happens when it's out of space?
Yeah, so the user can configure how many bits we should use for each packet. And the idea is that you're going to give me the set of queries. You're going to tell me how many bits per packet you want to add to that. And the PINT query compiler would figure out what fraction of the packets should serve each query and how many bits it should allocate to each. So we would never exceed the overhead that the user defined. If the lower the overhead is going to be, just the worse approximation you're going to get, and vice versa.
Okay, thanks. Oh, there's another question. So it asks, how much benefit can PINT bring if operators enable jumbo frame?
So I think like jumbo frame is not a silver bullet here. So even if you use jumbo frames and you add the INT information, it would add latency. And still, like, yeah, you're right that in terms of how many, like what fraction of the packets we can save by reducing the bit overhead, it's not going to be as much, but the other effects are still going to be the same. So the increase in latency, and also we can still use fewer packets to figure out the path and things like that.
Okay, thanks. Actually, I have a question. For your presentation, I can feel that, to kind of reduce the overhead of the metadata, you have to know what kind of a process you are doing with the data, right? Like how the end host use the data. Like you give 2 cases, one is HPCC, and how HPCC use the data is given. And also, for the path stuff, how the end host will extract the information and construct the path is given. So it seems that you have to know how people will process the data, and then you design a PINT to optimize that. Is that true?
So I think like the two things here. One is you need to know the set of queries you want to run in advance. If you want to run HPCC or you want to run path tracing, you need to know that. But there's two options here. So for HPCC, you need the end host participation, right? You need it to tune the sending rate. But for the path identification, this is something we do at the collector, same as an INT, and there we control everything. Like it's completely transparent to the end host.
Okay, thanks. There's another question. So basically, the question is, since you are using a probabilistic approach, so are you assuming the path is sufficiently long, to make the result stable? When the path is changing quickly, how it happens?
So we have an option to identify when the path changes, but you're right that if we need some number of packets, let's say 10 packets, to figure out the path, and the path is so unstable that it changes quicker than that, we wouldn't be able to get the path. But as long as the path is stable for 10 or 20 packets, we should be able to identify the path.
Okay. I have another question, actually. So have you implemented with the kind of like hardware? So it seems that, in PINT, there will be a lot of heavy computation, or not very heavy, but not very friendly to hardware. So I just wondering whether you see any kind of overhead or in your implementation.
So our current implementation is in a P4 simulation, but I think like the operations that are not natively supported and you would need in PINT are like multiplication and division that we use in the HPCC formula. But what we actually do in PINT is we give you some way to approximate it on the data plane. And you can think of it as another source of error, because like PINT is already an approximation algorithm. So the fact that we have another source of error coming from this approximate operations, you can still bound the overall error that it would create.
Okay. Well, I think the new question is similar to mine. I think somehow, do you want to add more? Or the question is, what's the overhead of probabilistic determination in the data path?
What's the overhead of what?
What's the processing overhead of the PINT in data path?
So it depends. So I think like for path tracing and our latency quantiles algorithms, it's going to be really minimal. So for the HPCC algorithm, it actually requires things like multiplication, and we approximate it using lookup tables that we store on the switch. And the larger the lookup table is going to be, the better the approximation would be. So there you do have some trade-off between the space and the accuracy.
Okay, I think the time is up. Thanks.
Okay. Thanks so much.